Hey everyone, welcome to another two-dimensional kinematics problem on relative velocity. Two cars approach a street corner at right angles to each other. Car 1 travels at a speed relative to Earth, v1e equals 45 kilometers per hour, and car 2 at v2e equals 65 kilometers per hour. Part A, what is the relative velocity of car 1 as seen by car 2? And B, what is the velocity of car 2 relative to car 1? Okay, so this is the diagram that's been given in the problem. You've got car 2 going in this direction, car 1 going in that direction. They're moving perpendicular to one another, and so I've established a coordinate system just to keep track of my directions, the northeast-southwest system, where I have established north and east to be positive. Okay, so moving on to part A. Okay, so let's get started on that. The relative velocity of car 1 relative to car 2. Okay, so everything is relative to this person right here. Now, if we're doing something relative to car 2, from car 2's point of view, they're not moving. Okay, but at the same time, if they're not moving, car 1 is getting closer to car 2, right? Because they're going towards each other like this. So car 1's getting closer to car 2. Car 2's not moving. Excuse me. Car 1 has a vertical component. The vertical component of car 1 is going to be going north, right? Because it's going up, it's getting closer. But when you compensate for car 2's direction, who's now stationary, you got to be careful, because if you state that now the horizontal component of this guy relative to car 2 is going east, technically he's going to be getting further away from car 2, right? Because this person's now stationary, we're assuming. Okay, so that means that the horizontal component actually needs to be going west. So we've got two components here. We've got a northward component and we've got a westward component. So car 1 has a vertical component, and that's north, and a horizontal component, west. Again, it can't be east, because if it's east and this person's assuming not to be moving, that means car 1's getting further away, but in fact we know they're getting closer to each other. Okay, so based on this, from car 2's point of view, there should be two vectors representing car 1's motion. Okay, so the vertical component is going to look like this. Let's do that down here. Okay, so that's going to be the velocity of car 1 relative to the street. Okay, and at the same time, remember that's the northward component. We've got a westward component that's compensating for car 2's motion, which we now assume to be horizontal. That's going to be v car 2 relative to street. And then finally, if these are the two motions, then the sum of those two, so you just add your vector, remember, from the tail of the first vector to the tip of the second, then we're going to have the velocity of car 1 relative to car 2. Okay, and those two are at a 90-degree angle because we've got a vertical horizontal component, and here's the angle that it's relative to. And you can see, based on this picture, they have to be getting close to each other. So now, in order to find this velocity, it's simply a right-angled triangle problem at this point. Right, so we can use Pythagorean theorem to solve this triangle. Okay, all you need is these two sides, and we can solve for the hypotenuse. So based on that, we can create the following formula. The velocity of car 1 relative to car 2 equals the square root of velocity car 2 relative to street squared plus the velocity of car 1 relative to street squared. Okay, c squared equals a squared plus b squared. That's what we're doing here. Okay, so now take a look at this. Car 1 travels at a speed relative to Earth at 45 kilometers an hour. Car 2 at 65 kilometers per hour. Okay, it's the same numbers. We're just doing it from a different point of view. Okay, so car 2 relative to street, that's still 65, but since we're assuming it to be going in the westward direction, that's what we declare to be negative here. So negative 65 squared plus positive 45 squared. And you can see here the signs really don't make a difference because you're squaring them. They're going to disappear anyways. And when you solve that, you get 79 kilometers per hour. So we need to do one more step. We need to determine that direction. So let's keep going with this. Okay, so based on our triangle here, we're going to use tangent because we know the opposite, we know the adjacent. Okay, so we're going to say tan theta is equal to 65 over 45. If you're wondering why I'm not putting the negative, it's because I'm simply finding the magnitude of this angle. I can establish the direction afterward based on my original coordinate system. Okay, so I'm just going to put in the numbers like this. So 65 over 45, so therefore theta is equal to the inverse tangent, and this thing comes out to be 1.44 repeating. And when you solve that, you're going to get theta is equal to 55 degrees. Okay, so based on our picture, okay, so let's move this down. Based on our picture, okay, so this is going north, this is going west, correct? So based on this picture, if the angle is 55 degrees, then that means it's 55 degrees westward of the north direction. Because you start at north and you angle yourself 55 degrees towards the west. So we can therefore express our final velocity. So therefore V car 1 relative to car 2 is equal to 79 kilometers per hour. And for your direction, you want to express this in square brackets, 55 degrees west of north. And there is your final answer for part A. So hopefully part A made sense to you. Part B is very similar. We're going to do the same thing, but from car 1's point of view. Okay, so for part B, we are instructed to find the velocity of car 2 relative to car 1. Okay, so now we're going to assume that this guy's not moving. So from this guy's point of view, they're still getting closer to each other, right? So car 1's not moving, they're getting closer. This car has a horizontal component now. It's east, right? Because he's moving east. And this car 2 also has a vertical component. And just like the previous one, we're not going to use the vertical component of this car 1 because if car 2 is going eastward and northward, he's moving away from car 1. So for this velocity, it should actually be going south. So we're going to have an eastward component and a southward component, which would ensure that they move closer to each other. So let's do that. So for part B, we're going to assume car 1 is not moving, and we're going to also assume that car 2 has a horizontal component, east. This is its velocity, by the way. And a vertical component, south. Okay, again, it has to be south because it's getting closer to car 1. So therefore, relative to car 1, we've got an eastward component and we've got a southward component. The eastward component comes from car 2 itself. So this is the velocity of car 2 relative to the street. And then we've got a southward component. That's from car 1. That's velocity car 1 relative to street. And when you add the two vectors together, you're going to get the velocity of car 2 relative to car 1. Okay, and again, these two meet at right angles. We've got our angle theta here. So it becomes a very similar problem to part A. Okay, so let's solve this. Pythagorean theorem, velocity car 2 relative to car 1 is equal to the square root of the sum of the squares of velocity car 2 relative to street squared plus the velocity of car 1 relative to the street squared. Okay, so car 2 relative to the street is going to be positive 65 because it's going in the positive direction. As per the velocity of car 1, it's going in a negative direction as per our original setup for directions. Okay, so this is going to be equal to the square root of positive 65 squared plus negative 45 squared. And it comes out to the same thing. Now, that has to be correct. They have to have the same relative speed compared to each other because they're both approaching each other, correct? So from either person's point of view, they should both be approaching each other at the same speed. Okay, so there's our speed. The only thing that's going to be different is the angle. Okay, so here's our angle theta. The angle has to be different because they are technically going at different speeds, although relative to each other, they look like they're approaching each other with the same speed. Okay, so in order to find that angle, we're going to go with tangent again. Tan theta equals 45 over 65. Again, I'm not putting negative signs because I'm just looking for the magnitude of that angle. So theta is equal to the inverse tangent of 0.692. And when you find that, you are going to get theta is equal to about 35 degrees. Okay, so based on our picture, take a look at that again. Okay, so theta is 35 degrees. We've got the eastward direction going like that. We've got the southward direction going like that. So you start at east and you go 35 degrees towards the south. Okay, or 35 degrees south of east. So that is our final answer. So therefore, the velocity of car 2 relative to car 1 is equal to 79 kilometers per hour, square bracket, 35 degrees south of east. And that's it for this problem, guys. I hope you enjoyed it. If you did, be sure to click that like button and subscribe to Physics in the Flesh so you never miss a video from me. I post every day at 12 noon during weekdays, so be sure to be on my channel at that time to catch my latest video. Enjoy the rest of your day, guys, and I will catch you in the next video.